Greetings everyone. Today I will be presenting our work entitled FCSA, an efficient carry speculative approximate adder with rectification, as a part of ISQED 2022. In this work, we have proposed a new reconfigurable approximate adder architecture that is based on the block division approach with carry prediction and inbuilt rectification. My name is Saurabh Singh. I am a fourth year undergraduate student at the Department of Electronics and Communication Engineering at the Indian Institute of Information Technology, Guwahati. So, without any further ado, let's start. Here is the outline of my presentation. First, I will give a brief introduction to approximate computing and how it can be employed in error-resilient applications. Next, I will discuss the motivation behind this work. Next, I will briefly describe the existing state-of-the-art works and their limitations. After that, I will present the proposed architecture and discuss its functioning. I will discuss the evaluation of proposed design and various trade-offs. I will also discuss the performance of design on end applications, and finally, I will conclude my presentation with a brief note on our team's future works. The ever-increasing requirement for information processing due to the advent of applications like machine learning, image processing, etc. has led to great demand for faster computers and therefore efficient chip architectures. It has been shown that applications like image processing, artificial intelligence, etc. are error resilient, meaning these applications can perform reasonably well within an acceptable range of errors in calculations. Therefore, research is already going on to explore this new paradigm of computing called approximate computing. Approximate computing exploits the error resiliency of such applications to improve upon parameters like computational speeds, hardware resource utilization, and power consumption. The use of approximations at various levels in a computer system can result in hardware level benefits across end applications. Since basic arithmetic blocks like adders and multipliers are core component of any computational unit, they are ideal candidates for approximation. Clearly, approximate versions of these circuits, when employed in error-resilient applications, can play a critical role in boosting overall system performance while sacrificing a little on accuracy. Furthermore, an approximate adder that can be reconfigured to behave as an accurate adder at runtime eliminates the need of an additional accurate adder circuit in the system to perform important accurate calculations. Several research studies on introduction of approximations over addition architecture have been published in past. Among them, REFCSA, SARA, BCSA, and ACA-CSU are the ones which we have compared our work. REFCSA is based on segmentation of carry look-ahead adder circuit into approximate and accurate parts. On the other hand, SARA uses a block-based approach towards the segmentation of ripple carry adder, with each block having a carry prediction circuit. Furthermore, BCSA also uses a similar approach of carry prediction, but additionally uses a carry select unit to select between accurate and approximate carry. ACA-CSU also uses a similar carry prediction and selection technique. Existing state-of-the-art designs often are non-configurable in nature, and therefore they can only cater to applications that have rigid accuracy requirements. Designs having near accurate results like BCSA ERU have a high power and area consumption, which makes them non-ideal for low-power applications. These designs often cannot be reconfigured at runtime and therefore often need an additional adder architecture to perform the necessary accurate calculations. Keeping the aforementioned points in mind, in this paper we have proposed a new adder design called FCSA, an efficient carry speculative approximate adder with rectification. FCSA features a faster approximation with the use of carry prediction logic and provides near accurate results due to inbuilt rectification. Let us now look at the proposed design. The architecture of FCSA adder is based on the traditional ripple carry adder circuit. It is aimed toward limiting the latency generated due to the long carry chain mechanism. The architecture is divided into n by k-bit summation blocks. The input operands of FCSA are segmented and are then fed into these summation blocks, and output from these summation blocks are concatenated, generating the results in a non-blocking parallel manner. Each summation block consists of a summation logic, a carry prediction logic, and two signals, namely ERGen and ERProp. The carry prediction for the next summation block is done by carry prediction logic of the preceding summation block. The ERGen signal is high whenever there is a finite probability of error being generated in the carry prediction. The ERProp signal is high whenever there is a finite probability of this error being propagated to the succeeding blocks. The logic formulation of carry prediction logic is based on these two signals and is shown in the following table. From a hardware point of view, the carry prediction logic uses multiplexer to select one of the signals among CA and CB. The summation logic consists of k-bit RCA to generate the sum and the rectification unit in form of a multiplexer to select the correct least significant sum bit. The ERProp and ERGen signals are used for deriving the select lines of these multiplexers. The FCSA adder can be reconfigured using an additional bypass circuit controlled by an additional input called the mode signal. This enables FCSA adder to be switched between approximate and accurate modes of computation at runtime. We call this version of FCSA as REFCSA. When mode signal is high, the accurate carry from ripple carry adder is selected as Cout and fed to the succeeding blocks. As a result, the adder becomes accurate as all the carry prediction circuitry has been bypassed. However, this flexibility to switch between the modes of computation comes at a cost of 43.59% larger on-chip area and 48.22% more power consumption. I will now discuss the evaluation of the proposed designs. All the adders used for the comparison have been implemented in Verilog RTL and synthesized using Synopsys Design Compiler with the NAND Gate 45nm open cell library. We have used MATLAB to perform error calculations and to obtain end application results. The plot on the right shows the on-chip area of all the adders in various configurations. On average, FCSA has 2.85% and 7.17% lesser area compared to REFCSA and BCSA ERU. However, SARA and BCSA consume 22.94% and 0.7% less area than FCSA. SARA and BCSA are efficient in terms of area and power, being less accurate than FCSA. Thus, we conclude that FCSA has a comparable area when compared to these existing designs. This slide showcases the trade-off between mean relative error distance or MRED, which is an accuracy parameter, and power delay product or PDP, which is a design parameter. Ideally, a design should have least MRED and PDP, which symbolizes high accuracy, low power consumption, and optimum delay. We observe that FCSA is 45.10% more accurate and has 31.97% lesser PDP than other designs, making it suitable for error-resilient applications. The most accurate configuration of the FCSA adder offers a PDP of 71.73, which is 40.98% less than REFCSA, 30.64% less than SARA, 59.40% less than BCSA, 61.05% less than BCSA ERU in their respective most accurate configurations. It is evident from the plot that FCSA adder has the best trade-off between MRED and PDP. This slide showcases the critical path delay of all the adder designs in various configurations. A design with minimal delay is considered optimal. We see that on average FCSA has 27.96%, 31.34%, 39.31% and 45.08% less critical path delay than REFCSA, SARA, BCSA and BCSA ERU respectively. It has 37.47% less delay as compared to other state-of-the-art designs. This delay improvement is a result from avoiding long carry chains present in the accurate adders and the inherent parallelism incorporated due to the use of a block-based segmentation technique. This slide showcases the trade-off between peak signal to noise ratio obtained from an image processing application and power delay product of the design. It is clearly evident that FCSA produces higher PSNR than SARA by 33.54%, REFCSA by 79.8%, BCSA by 28% and ACA-CSU by 15.4%. At the same time, FCSA has PDP of 71.73 nanosecond times micrometer square, which is 40.98% less than REFCSA, 30.64% less than SARA, 59.40% less than BCSA. We conclude that FCSA mostly produces desirable images as the PSNR values are greater than 40 decibels, while consuming a fraction of PDP compared to the state-of-the-art designs. We have evaluated the performance of our design on two classes of applications, image processing and machine learning. In this slide, I will discuss the results obtained on Gaussian smoothing application, which is an image processing application. We have used 32-bit versions of all the adders with a block size of 8 bits. To evaluate the quality of obtained images, we have used peak signal to noise ratio or PSNR and structural similarity index or SSIM as key parameters. Generally, PSNR values higher than 40 decibels are considered good. The table at the bottom shows the PSNR and SSIM values obtained using various adders on Gaussian smoothing application. We use a 5x5 Gaussian kernel and 256x256 grayscale images of Lena, chemical plant, and moon surface for this purpose. Using FCSA, we obtain a PSNR of 44 decibels on Lena, 40.4 decibels on chemical plant, and 44.9 decibels on moon surface image. It is evident that FCSA performs consistently well across all the images, delivering an average PSNR of 43.1 decibels. We have also evaluated our design on two machine learning applications, namely k-means clustering and k-nearest neighbor. In the k-means clustering application, we used a dataset of 150 points uniformly distributed into 3 clusters. We have used a metric called relative accuracy, that is defined as the number of data points clustered accurately in comparison to the baseline. 32-bit FCSA with a block size of 8 produces the results with relative accuracy of 96.67% to the baseline. REFCSA, SARA, BCSA and ACACSU with similar configurations have respective relative accuracy of 60.67%, 41.34%, 52% and 97.3% compared to the baseline case. In the k-nearest neighbor application, we have used several integer datasets including Monk's problem, Haberman's survival and letter recognition. We have used the Euclidean distance metric for similarity calculation. In the KNN applications, we see the only deviation in terms of accuracy by a magnitude of 0.92% in case of Haberman's survival. Rest all datasets perform exactly like accurate adder, both in terms of accuracy and F1 score. In conclusion, this work proposes FCSA, a novel architecture for approximate addition of two unsigned numbers. A reconfigurable version of FCSA called REFCSA has also been proposed along with this work. FCSA uses a block-based approach towards segmentation of conventional ripple carry adder circuits and exploits the input bits to predict carry through carry prediction logic. Block level parallelism and carry prediction technique in FCSA helps to limit the carry chain length, providing significant computational speedup at the cost of marginal area overhead. It also incorporates an error rectification scheme that modifies the error-prone sum bit at various bit locations. In future, we wish to investigate this reconfigurable addition technique on higher architecture sizes and floating point arithmetic in order to evaluate the implications on performance and hardware characteristics. Thank you.